I am Dr. Anubha Gupta from ABES Engineering College, Ghaziabad. I am presenting lecture series on electromagnetic theory. This is the part 3 of my lecture series. In the previous lecture series, I already covered about displacement current, Stokes theorem, Gauss theorem, Maxwell first, second, third, fourth equations in a differential and integral form, displacement current, and in this part 3 topics to be covered, Pointing vector and pointing theorem. This is a very important topic of electromagnetic theory. So first of all, we will understand that what is the meaning of pointing vector. So the rate of flow of, this is the pointing vector, the rate of flow of energy per unit area from the surface of the medium is known as pointing vector. If the rate of flow of energy from the surface area from the per unit area from the surface is known as Poynting vector. It is calculated by the cross product of vector A and the magnetic field vector H. It means it is denoted by S. It is denoted by S. Vector S, and it is given as cross product of electric field and magnetic field. The unit of Poynting vector is watt per meter square. And the direction of the Poynting vector is the same as the direction of propagation of the wave. So I am going to drive the Poynting theorem. When electromagnetic wave travels from one place to another place in space, as a result, energy also transported from one point to another point. Poynting theorem, also known as work energy theorem. The another name of the Poynting theorem is work energy theorem. So I am going to prove the Poynting theorem or work energy theorem. This Poynting theorem will start from the Maxwell third and fourth equation. We know Maxwell third and fourth equation. Del cross E is equal to minus mu del H by del T. This is equation number third. And equation number 4, del cross H is equal to JC plus epsilon del E by del T. This is the Maxwell third equation and this is the Maxwell fourth equation. So I will take it as equation 1 and 2. Now, taking dot product of H and E, vector H and vector E, on both sides of equation 1 and equation 2 respectively. Means again I am writing the equation number 1, del cross E is equal to minus mu del H by del T. And the equation number 2 is del cross H is equal to JC, conduction current, plus epsilon del E by del T. This is the equation number 2. So taking the dot product of H on both sides of equation number 1, minus mu H dot del H by del T. And this equation and we will divide by the vector E on the both side of equation number 2. Cross H E dot JC plus epsilon E dot del E by del T. This is the equation number 2 and this is the equation number 3. Now I will subtract equation 2 minus 3. Equation 2 minus equation 3. And I will get H dot del cross E minus E dot del cross H is it is equal to minus mu H dot del H by del T minus E dot J minus, it is not equation 2, it is equation 3, and this is equation number 4. So I am going to subtract equation 3 and equation 4. Equation 4 from the equation number 3. So it become epsilon E dot del E by del T. And this is the vector identity. This is a vector identity which is equal to del dot E cross H. This is the vector identity in which the del B dot A cross C is the BAC minus CAB. So this is the vector identity. Divergence of E cross H is equal to minus mu H del H by del T minus epsilon E dot del E by del T minus E dot J. So in this equation, suppose this is the equation number 5. Now, what can we write this term? Minus mu H del H by del T. This term can be written as mu by 2 del H square by del T. Because if I will differentiate H square in terms of del T, I will write 2H del H by del T, and mu by 2 is the constant. So this 2 will be cancelled out by this and it become mu H del H by del T. So I can write this mu H del H by del T as mu by 2 del H square by del T. And similarly, this term epsilon E dot del E by del T can be written as epsilon by 2 del E square by del T. If I will differentiate this E square, it will be 2E del E by del T. And this 2 will cancel out. So these both equations are same. So it can be written like this. So this mu H del H by del T is equal to mu by 2 del H square by del T. So equation number 5 becomes del dot E cross H. This is the left hand side of equation number 5 is equal to. Equation 5 becomes, and this is the first term. It can be written as minus mu by 2 del H square by del T minus epsilon by 2 del E square by del T minus E dot J. We can write these terms like this. It is in the form of stored electrostatic energy and stored magnetostatic energy. Now taking volume integral, this is the equation number 6. Now I am taking volume integral on both sides of equation 6. It becomes divergence of E cross H of dV minus mu by 2 del h square by del t plus epsilon by 2 del square by del t dv minus E dot J dv. Now we will apply the Gauss divergence theorem here. We know divergence of any vector over a volume integral dv can be converted into E cross H ds. And I will write these terms as it is. So it becomes E cross H after applying the Gauss divergence theorem on the left hand side, and the right hand side will be minus mu by 2 del h square by del t plus epsilon by 2 del e square by del t into dv minus E dot J dv. This is the pointing theorem where E cross H ds after applying the Gauss divergence theorem. Now I will rearrange all the terms. After rearranging, it becomes E dot J dv is equal to minus mu by 2 del h square by del t plus epsilon by 2 del e square by del t dv minus E cross H ds. This is the term 1. This is term 2. And this is the term 3. Every term has physical significance. Term 1 has physical significance that it represents power dissipated per unit volume. Term 2 represent stored electric field and magnetic field energy per unit volume, which appears in the form of heat. This is the term 3, and it represents the rate of flow of energy per unit area of surface. It is also called as Poynting vector. And for this, this is called the work energy theorem or Poynting theorem. This is the expression for Poynting theorem, which show is equal to the stored energy in the form of electrostatic and magnetostatic form, and the power and or the rate of flow of energy per unit area of the surface. And this is Poynting theorem. The references of my presentation: Introduction to Electrodynamics by David J. Griffith, Solid State Physics by S.O. Pillai, and Engineering Physics by S.K. Gupta. Thank you for patience listening.